Changes in the membrane potential can either be what we call graded potentials or action potentials. Graded potentials are going to be localized changes in the membrane potential. Typically, these are going to be in neurons what we call postsynaptic potentials because they are going to be caused by the release of neurotransmitter at a synapse. These postsynaptic potentials, these localized graded potentials, can either be excitatory, typically due to the opening of sodium channels, which is going to cause sodium to flow in and make the cell less negative, more positive, depolarize. So here we see we're going towards 0 for our excitatory postsynaptic potentials, or they can be inhibitory. Inhibitory postsynaptic potentials, IPSPs, are going to involve either the opening of chloride channels or potassium channels. Chloride is going to be at a high concentration outside of the cell, and so chloride is going to want to move into the cell, especially as the cell becomes more positive. Normally, the negative charge inside of the cell is going to repel chloride, but if the cell starts to depolarize, become less negative, it's going to stop repelling chloride. Chloride's going to move in and make the inside of the cell more negative again. Potassium is at a high concentration inside of the cell, so the more potassium channels open, the more potassium is going to leave the cell, and the more negative the cell is going to get. Remember, that's how we actually generate the membrane potential to begin with. In a graded potential, the current is going to flow. Remember, current is going to be the movement of charged particles, but it's not going to last long, and it's not going to spread very far. Graded potentials are only going to travel across short distances before dissipating. However, graded potentials can undergo what's called summation. So this is where multiple graded potentials get added together. Excitatory action potentials get added together. Inhibitory postsynaptic potentials get subtracted, and if that overall adds up to reaching threshold, then an action potential is formed. So an action potential is this self-propagating wave of depolarization that spreads down an axon. And they move very quickly, and they send messages over long periods of time. They don't decay over distance as graded potentials do. They are always going to have the same intensity all the way down the axon. This is going to happen once there's enough depolarization of the cell for it to reach that threshold potential. Action potentials are going to follow what's called the all or none principle. All action potentials in a cell are the same. Each action potential has the same change in voltage as a previous action potential. There's no such thing as a big action potential or a little action potential. Either a cell fires an action potential or it doesn't. The actual intensity of the signal is determined by frequency, not by size of depolarization. Here we have graded potentials, so the summation of those postsynaptic potentials, if it reaches threshold, then we fire an action potential, where we have this big depolarization, and then we are going to have a repolarization. Note this action potential doesn't occur in just one spot in the cell, it actually spreads all the way down the axon. So how do we generate an action potential? So at our resting state, our voltage-gated sodium channels and our voltage-gated potassium channels are closed. They're voltage-gated. However, once the cell reaches threshold due to the graded potentials, then the voltage-gated sodium channels open. That's why it's called voltage-gated. It opens once the cell reaches a certain voltage. The opening of the voltage-gated sodium channels causes an influx of sodium. So the sodium is going to move into the cell, and it is going to make the cell less negative, and that's going to trigger the opening of other voltage-gated sodium channels. And so we're going to have this big depolarization. Once we've depolarized, then we need to move on to repolarization. Once we hit this peak voltage up here, this peak depolarization, then the voltage-gated sodium channels inactivate. They don't just close, they turn off completely. So now sodium stops flowing into the cell, and then we are going to open up voltage-gated potassium channels. So now potassium is going to leave the cell. Note at this point the inside of the cell is actually positive, so we have both the electro and chemical gradients forcing potassium out, and so potassium leaves the cell very quickly, repolarizing the cell. Because the cell is more permeable to potassium than normal at this point, we actually undergo what's called hyperpolarization. We go slightly more negative than necessary, or than normal. We actually need to do this in order to reset the voltage-gated sodium channels. The voltage-gated sodium channels won't open back up until the cell hyperpolarizes. At that point, the sodium channels don't necessarily open back up now, but they stop being inactivated. They can open back up and fire another action potential. So, in order to fire an action potential, we reach threshold voltage. At threshold voltage, we are going to have the opening of voltage-gated sodium channels. Sodium flows in. We get depolarization. Once we reach that peak of depolarization, the voltage-gated sodium channels inactivate, turn off. We stop getting sodium moving into the cell. Voltage-gated potassium channels open up. Potassium is going to leave the cell very quickly, repolarizing, and because the cell is more permeable to potassium than normal, we're actually going to hyperpolarize, become more negative than normal, which is what is going to reset the sodium channels so that they can open again to form another action potential if the cell reaches threshold again. There we go. So, graded potentials reach threshold. Then once we reach threshold, voltage-gated sodium channels open, causing the rapid depolarization. At the peak of the depolarization, the sodium channels inactivate, potassium channels open, the cell repolarizes, and then actually continues past and hyperpolarizes, and then the cell will eventually return to normal and be ready to send another action potential. Action potential, as it travels down the axon, is self-propagating. The opening up of sodium channels causes a sodium current, which depolarizes that area and causes nearby sodium channels, voltage-gated sodium channels, to open and depolarize that area. Note, while this area is depolarizing, the previous section is actually repolarizing. Sodium channels are closed and inactivated. Potassium channels are open. So, this is going to prevent the backward spread of an action potential. Action potentials only move one way, down the axon from the cell body, from the axon hillock, to the axon terminals. Doesn't move the other way because these sodium channels, after opening, inactivate. So, sodium channels open, sodium flows in, depolarizes this area of the axon, triggering the opening of sodium channels in the next area of the axon, which is going to depolarize that area and trigger the opening of sodium channels in the next area of the axon, which is going to depolarize that area. And this continues all the way through. The section that had just been depolarized is then going to go into repolarization, and while that's happening, the sodium channels are inactivated, so the action potential cannot spread back, only forwards. After an action potential, we are going to have what's called a refractory period. This is going to be a period of time when the neuron will not fire another action potential. Note, this is a very, very small period of time. It's measured in milliseconds, but it is still there. And we can divide it up into what's called the absolute refractory period and the relative refractory period. The absolute refractory period is the period when either the sodium channels are open, and so we are forming an action potential, and when they are inactivated, or when they reactivate. So remember, hyperpolarization is what actually resets the sodium channels. So during this period of time, we absolutely cannot generate a second action potential because either we are in the middle of depolarizing already or the sodium channels are inactive. Once we hit hyperpolarization, we enter the relative refractory period, where the cell is just much, much less likely to fire another action potential because there are still potassium channels open, which makes it hard for the cell to depolarize. Once the cell goes back to its normal resting membrane potential, it is ready to fire another action potential. Remember, action potentials all follow what's called the all or none principle. So each action potential has the same change in membrane potential. In order to have stronger and weaker stimuli, the central nervous system instead is going to rely on frequency of action potentials. A strong stimulus has a lot of action potentials. Strong stimulus has a lot of action potentials. Weaker stimuli have less action potentials, and subthreshold stimulus doesn't generate action potentials. Actually, in reality, the cell randomly fires action potentials even when unstimulated, so there's some action potentials, it's just at a very, very low frequency. Different axons conduct action potentials at different speeds. And that is going to be based off of how quickly current flows down the axon. And the speed at which current flows down the axon is going to depend on two factors: axon diameter and myelination. When you increase axon diameter, you decrease resistance. And so the sodium current is able to flow faster and farther. And also, degree of myelination. This is going to insulate the outside of the axon, and that is going to allow for the current to travel further without dissipating inside of the axon. The degree of myelination is going to cause us to have two different types of what's called conduction inside of the axon, which is that spread of the action potential down the axon. Note, changes in the speed of nerve conduction is associated with certain diseases, so we can actually measure this. The ways that the action potential can travel down the axon is either as what we call continuous conduction or saltatory conduction. Continuous conduction is going to occur in unmyelinated fibers, whereas saltatory conduction is going to occur in myelinated fibers. So in continuous conduction, there's no insulation on the outside of the axon, which means that the current is going to lose its voltage relatively quickly. So the signal has to be constantly refreshed. I like to think of this as walking by taking a whole bunch of baby steps. So because the signal has to constantly be refreshed by reopening voltage-gated sodium channels, this takes time, and so we have to take a whole bunch of tiny little steps, many, many little steps. So it's not that fast. In saltatory conduction, we are going to have myelin that's going to insulate the outside of the fiber. That allows the current to spread farther and faster. And so it only needs to be refreshed at these myelin sheath gaps. Remember, I told you they were important. So this is going to be where we refresh the signal. So the signal goes from one point to the next gap in the myelin sheath to the next gap in the myelin sheath. Because it jumps, it's called saltatory conduction. Saltatory actually means jumping. This is like taking great big steps instead of continuous conduction, which is taking tiny little baby steps. In multiple sclerosis, this is going to be an autoimmune disease where the immune system attacks the myelin. And it attacks the myelin and converts the myelin into what are called scleroses, which is why it's sclerosis. And this is going to slow down the rate of conduction because we're no longer, without that myelin, the cell has to rely on continuous conduction instead of saltatory conduction. The signal is now taking baby steps down the axon instead of great big steps. And this causes a lot of issues with sending signals. So this can cause visual disturbances, muscle weakness, lack of muscle control. It can make it difficult to speak and swallow, and also can lead to incontinence. So treatment is going to involve drugs that are going to help prevent the immune system from attacking the myelin. Different fiber types inside of our body have different properties which affects the conduction speed. So what we call group A fibers have a large diameter and are heavily myelinated, which allows it to send signals very, very quickly. So this is going to transmit at 150 meters per second or about 300 miles per hour. So very, very fast. Group B fibers have a smaller diameter than group A fibers and are less myelinated, so they're going to transmit significantly slower, only about 15 meters per second or about 30 miles an hour. Group C fibers have tiny little diameters and they're completely unmyelinated, and therefore they're going to have the slowest rate of transduction, so they are going to transmit at about 1 meter a second or about 2 miles per hour. We're going to use our group A fibers for somatic sensory and motor fibers because we need rapid responses for this. B and C are going to be used for visceral motor and sensory fibers. So with our somatic sensory fibers, remember this is going to be voluntary actions. This is going to be responsible for things like evolutionarily noticing prey, following the prey, attacking the prey, noticing that you are being preyed upon, running away from a predator, things that happen very quickly. Group B and C are more visceral responses that don't have to happen as quickly because after you've eaten a hamburger, it's important to monitor what's happening with that hamburger, but it's probably not going to try to escape after it's already inside of your guts, right? So visceral effects tend to occur on a much slower time frame than our somatic effects.